Now we're going to look at the conservation of mass principle. Someone give me the definition. Right. So Izzat says, so this is one of the answer. This one, right. So these are the apa ni? Some of your friends uh, definitions, I guess. Conservation of mass principle is that mass of body remain constant, right? So this one, when you said about mass, we are looking at the closed thermodynamic closed system, right? So we have mass inside a container, for example, and the container is moving, so the mass is always remain constant, does not change. And the other one can say that the conservation of mass principle says that the rate form as the rate of change of time of the mass being zero, rate of change with time, rate the rate of change of the mass of the body remains zero. So it says here the rate of change um, remains zero. It means that the mass of the system uh, does not change with time. So there is a gradient of mass, right? So it can be positive, it can be negative. If positive means the mass is accumulated inside the system. If the rate of change of mass with time is less than zero, it means there is mass losses. So this one is a statement. We can write them inside as an equation. Um, yes, I can express mathematically. So let me show you how it's possible to have that. So in terms of a concept there, right? So we have the concept here called accumulations, right? What are the terms that represent that equation? And then this one, and then we have flow. Um, Actually, this one is represent the system in the system, right? When we define our domain scope of solutions, and then there is a mass in. Just now in the previous session, we look at the mass flowing in and mass flowing out, right? So we have the generation of mass within the system, and then some of them is lost, and then we have the accumulated within the system. Let's say, for example, we have a balloon, right? So let's say you have a balloon. Let's say I like a red balloon, right? Before, and then we put some air inside, so it become right. So we have and then we have the next information that you can get from the internet. It says that this principle, the engineering principle, says that the system in a container um, is remain constant. So we are always talking about a system in a container, and then the mass cannot be added nor be removed. And it's very interesting, the definition, right? This one been used. So it's very interesting. What does it mean? Neither be created, cannot be destroyed. What is this mean? If you are human, right? So he said that the principle of conservation of mass state that if the earth is empty, then the man cannot be created, the man cannot be destroyed. So this very dangerous statement here. So, and cannot be produced mathematically, right? So I don't think that you should use this statement in my class lah. Don't use this statement because it will distorted people punya akidah. So better not to use that. Right, this one you're not going to use that definition. Okay, so this conservation of mass principle can be written in two different forms. Right, let me copy that one again. The first one based on microscopic approach is based the one that your friend had mentioned just now. This equation called mass balance, right? So mass accumulation rate, which is the m per dt, right? The mass, the time rate of change of mass in the system divided by time. So let's say you have a balloon. So this mass is inside a balloon, and then you blow in some air, so there will be mass flux. So mass flux is the mass flow rate divided by area. That means divided by area, right? So we have dot there. Dot there, right? So the unit is kilogram per meter square, square meters times second. So that the mass flux, right, that coming in. So what is represent this mass flux? So it represent a single point, right? So we just copy that again. So the mass flux actually represent one single point. So you have a velocity that enter this point, so that will represent a mass flux. So you have mass flux coming in. If you integrate the whole, you get this rho VA, right? So and then we have minus those leaving for the balloon. There is no outlet. So whatever the mass of air that enter the balloon, it will be accumulated in the balloon, right? So that will represent the mass accumulation rate. And then in the balloon, we don't look at the mass reaction. This one react chemically with the material for the balloon material, and they produce additional air, for example, right? So in our course, we're not going to consider chemical reactions. We just consider the mass coming in and then mass leaving out, that accumulated rate. And we're not going to, in the class, we're not going to consider this part, right? So this one will be considered as 0 in our case. So so this one will be 0 in our engineering assumption, right? So our engineering assumption, so we are looking at the steady flow processes, right? So when we assume steady flow processes, there is no mass accumulation rate for the problem that we're looking at. But if you want to work on assignment, that you want to look at the event when there is a mass accumulation rate, there is no problem. You can do that. Yes, Lukman. Ada apa, Lukman?
Tak apa sir, salah tekan.
Ha? Tak ada apa, salah tekan.
Salah tekan sir, sorry.
Jangan tekan-tekan. Nah, tak perlu tekan-tekan.
Test.
Nak test. Tak puas nak test so there's a mass flux there, right? So I just put it again. Dah lupa saya dah mass flux. At that particular point, okay. So this is another concept. yang you belajar hari ni, that you learn today. So most of the time we're going to consider M in minus M out, right? So this is based on microscopic approach. The resulting equation based on the microscopic approach is called mass balance. So remember that this is a name of equation, right? There is another microscopic approach that is based on the equation that we produce. That will be based on the very small tiny particle inside the domain, right? So let me print that thing. So we are consider a very small domain there, right? Copy this, right? They say it's very small domain that plays inside the domain, and then we uh, make it larger. So this based on microscopic approach. So we are evaluating this small element that you can call particle inside. So there is a volume there. We have dimension in x, dimension in y, and dimension in z, right? So but this the volume still larger than the motion of a molecule inside the domain, right? um, and then the resultant equation is called continuity equation. So if we consider a two-dimensional problem, so we have we assume that there is no flow in z direction, right? So we just consider the fluid that moving um in x direction, coming in and leaving, and then there is a fluid that coming in y direction and then leaving in y direction. So we have the partial differential equation that represent the conservation of mass principle for very small volume, right? So what does this mean? This equation mean, right? So this what it is a net mass uh, net mass flow rate in x direction. This one. Oh, right. And then we have the net mass flow rate in y direction. So that will be this equation, this term. And then we assume there is no mass accumulated in very small domain. So there is no accumulation. When you said that this one is 0, there is no mass accumulation inside this domain. So I just want to conclude. So for this session, we are looking at the conservation of mass principle, right? So we have a macroscopic approach, and then we have a microscopic approach. So here we obtain the equation that called mass balance, right? So in our course, we're going to look at this mass balance macroscopic approach when we want to evaluate the force acting on the pipe. And then we can use the microscopic approach here to determine the velocity distribution inside the pipe. So the purpose that why we will have to learn about this microscopic approach in order for us to determine the velocity profile in the pipe. Right. So you can use also computational fluid dynamics to determine the velocity profile as well. So any question before I finish? End of class here. So in our level, we have to compute the mass flow rate in both direction. No, no, no. So in your case, as I said, we just consider a pipe flow. So pipe flow only consider that the fluid that coming in and leaving through the axis of the pipe. So it means there's only one dimensional flow. This video will be recorded, right? I hope I recorded it. Um, um, but you still can get the slide information, and I'm going to give you the link to the file, to the videos, so that you can download.